So let's talk about one of the most basic things we ask a computer to do. Just make a list. Sounds easy, right? I mean, how hard can it be? Well, as we're about to find out, there's a surprising and kind of complicated story hiding inside this super simple task.
Seriously, think about it. Your to-do list, your music playlist, the contacts on your phone, even the words in a document you're typing. They're all just lists. But the way a computer actually builds that list can be the difference between an app that feels snappy and instant and one that just lags. So what is going on under the hood?
All right, to get to the bottom of this, we need to meet the first character in our story. We're going to call it the digital bookshelf. In the programming world, though, it goes by the name ArrayList. Now, you should picture an array list exactly like it sounds, a perfectly neat bookshelf. Every single book, or every piece of our data, it has its own numbered spot, sitting right next to its neighbors in a perfect row. The computer knows exactly where that shelf starts in its memory. So if you say, hey, get me book number 50, it doesn't have to search around. It just does a tiny bit of math, calculates the exact spot, and boom, grabs it instantly.
And that right there is the ArrayList's superpower, its speed. Getting or changing any single item is lightning fast because everything is so predictable. This side-by-side storage is incredibly efficient if all you're doing is reading data. But, and this is a big but, it has a hidden weakness.
And this is where the plot thickens. That beautiful, orderly bookshelf, it has a secret flaw, a problem that pops up the second you try to mess with its perfect order. So, what does happen when you decide you want to slide a new book into the middle of your perfectly organized shelf, right? You can't just put it there. There's already a book in that spot. You've got to make some room.
Okay, take a look at this list of numbers. It's a nice, neat row, just like our bookshelf. Now, let's say we need to insert the number 29 right into the third position, where 31 is currently sitting. Seems like it should be simple, but for the computer, it's about to become a whole lot of work.
This is the problem in a nutshell. To make that one empty spot, the computer can't just magically shove everything over. Nope, it has to go all the way to the end of the list, grab the very last item, and physically move it one space over. Then it goes to the second to last item and moves it. Then the next, and the next, and the next. It's this massive, slow domino effect that ripples all the way back to the spot we need. It's only after all that shifting that we can finally place our new number. And believe me, this isn't just a theoretical headache. The source material spells it out. On a big list, just one simple add or remove operation can force the computer to execute thousands of these individual shift instructions. Every single one of those takes up precious time and processing power. Now just imagine that happening over and over again.
So let's put a real number on this, on the true cost of all this shifting. It is a really, really big number. 3.75 billion. What on earth could cause that many operations?
Well, there you have it. That's the cost. In one test, just making 7,500 small changes to a big list, think about editing a large document or rearranging a long playlist, it forced the computer to perform over 3.75 billion shift operations. This is exactly why an app sometimes stutters or even freezes when you're just trying to move things around. You're seeing the great shifting problem in real time.
Okay, so if our bookshelf is this flawed, there has to be a better way, right? Well, there is. And now it's time to meet the hero of our story, a much more clever and elegant solution called the linked list.
A linked list completely throws out the whole idea of a neat side-by-side bookshelf. Instead, it's way more like a scavenger hunt. Each item in the list holds two things. First, its own data, and second, the exact address in the computer's memory of the next item in the list. The items themselves can be scattered all over the place. It doesn't matter. All that matters is that each link in the chain points to the next one correctly. So how does this scavenger hunt fix our massive shifting problem? It's actually beautiful. Look here. Initially, item A's clue points straight to item C. Now, to insert our new item B in between them, all we do is a little bit of rewiring. We tell item A, hey, from now on, you point to our new item B. And then we tell item B, okay, you're going to point to item C. And that's it. We're done. The chain is relinked.
Did you catch that? We didn't have to move item C at all, or D or E or anything that came after it. No massive domino effect, no billions of operations. We just changed two tiny little pointers. It is an unbelievably efficient way to add or remove things from a list.
And all of this leads us to the final chapter, the dilemma. Because now we have two totally different ways to build a list, and each one has its own killer feature and its own crippling weakness.
This creates a classic trade-off that every programmer has to face.
So let's break it down one last time. The array list, our bookshelf, is amazing for reading. You need item 500? Boom, you got it instantly, but it's painfully slow for adding or removing stuff. Then you have the linked list, our scavenger hunt, which is the complete opposite. It is incredibly fast for adding and removing items, but if you want to find the 500th item, you can't just jump there. You have to start at clue number 1 and follow the chain all the way through 499 other items just to get to it. One is a reader, the other is an editor.
And that is the fundamental question, isn't it? There's no single best list. It all comes down to what the list will be used for. Are your users mostly going to be reading information, or are they going to be constantly editing and changing it? Understanding this hidden cost, this deep trade-off between the bookshelf and the scavenger hunt, that's what makes the difference between good software and great software. The choice is everything.